This is the fourth section of, and the final section of chapter 6, further hypothesis test, and this section is on the F test. So what we do in this section is we carry out a hypothesis test to see if the variances of two populations are equal. Now, when I go through this, every time I refer to population X, it's going to be the population that has the largest sample variance, and population Y is going to be the population that has the smaller sample variance. So in a question, you'll be given two sample variances, and whenever I refer to X here, it's the one with the largest sample variance. So we need to look at those two numbers first before we move any further. So the first thing we need to do is to write down H0 and H1. Now H0 and H1, H0 is always going to be that the population variances are equal. This needs to be the population that has the largest sample variance, so population X. H1 can be in two forms, that the population variances are not equal to one another, like this. Now in this case, it will be a two-tail test, and actually it won't be a two-tail test, it's only going to be an upper tail test, but we do need to divide the significance level by 2. So it's basically, we only need to test the upper tail, so maybe it might be better to write that. Okay, so it's a two-tail test, so let's write that down. So yeah, as I said, it's a two-tail test, but we only need to test the upper tail. That still means that we divide the significance level by 2. So you don't need to find a lower critical value and test at that end, and you'll see why in a moment when we look at our test statistic. And then the other form of H1 would be that the variance of population X is greater than the variance of population Y. So this is a one-tail test, and this will just be like an upper tail test. So again, what we have here is that the first population, this is the one that's got the largest sample variance. Next, we want to work out our test statistic, and that's going to be our sample variance of X, the one with the larger value, divided by the sample variance of Y. Now, because it's always going to be a bigger number at the top than the bottom, there's going to be a tendency for this value to drift towards the upper tail if there's a significant difference between these variances. So as the difference between these sample variances increases, the value of the fraction increases, so we're drifting towards the upper tail. So that's why for not equal, we only need to look at the upper tail. We still split the significance level, but we only work out an upper critical value. So next we need to find our critical value. At this point I often draw a sketch, and I'll be working out this value here, critical value. This area is either going to be 5% or 1%, and it will be an F distribution with 2 degrees of freedom. We need to watch out which way around we do it. The first degree of freedom is going to be n minus 1 of the larger variance. So whichever one of my populations has a larger variance, so in this case my population X, I look at the sample size of that variance, the sample size n, subtract 1, that will be my first value. My second value, nu2, is going to be the n from the population with the smaller sample variance, so however many were in that sample minus 1. So larger variance n, smaller variance n, or larger variance n minus 1, smaller variance n minus 1. So make sure you don't mix those up. And then once we've found our critical value, we can decide whether our critical value is not in a critical region, so it may be somewhere over here, or is in the critical region. And at that point we can say whether we're going to accept or reject H0, and then come up with a conclusion about the population variances, whether there's evidence to suggest the population variances are the same or not equal to each other, or the population variance of one is greater than the other. Example 9. Two samples of sizes 13 and 9 are taken from normal distributions x and y with variances sigma squared x and sigma squared y respectively. The two samples give values of 24 from the x population and 18 from the y population. Test at the 5% level and it gives us H0 and H1 here. So since population X has the larger variance of 13, H0 and H1, they're in the correct format with the larger variance written first, the larger variance greater than the smaller variance. Now we're going to work out our test statistic, which is the larger variance divided by the smaller one, so the variance of 24 divided by 18. And that's 1.3 recurring, so let's just call it 1.33. Now I'll work out my critical values. I've just drawn a diagram here. Because it's greater than, this is going to be an upper tail test, and it's at the 5% level, so this area is 5%. So I only need to work out a upper critical value. And the upper critical values are the ones where you just read them from the table. So I'll need to know my degrees of freedom for both populations. So for the first population, let's call this X here. So my first one, that'll be 1 when I put it with my F distribution. It's 13 minus 1, which is 12. And then for my Y distribution, or population, that's going to be 9 minus 1, so that's going to be 8. So I'm going to be looking at F distribution with 12 and 8 degrees of freedom, and the area to the right, which exceeds my critical value, is going to be 0.05. So let's see what this gives us from the table. So 12 across and 8 down from the table gives me 3.28. So this is my critical value. So this value here is 3.28, and my test statistic is going to be somewhere over here, not in the critical region. So we need to show that. So we'll say that 1.33 is less than 3.28, therefore not in critical region. I'll just write CR. So not enough evidence, or insufficient evidence to reject H0. So what does that mean in the context of the question? The variances are the same. Or we could just literally write down that variance of X equals the variance of Y. Example 10. Two samples of sizes 7 and 11 are taken from normal distributions X and Y with variances sigma squared X and sigma squared Y respectively. The two samples give values, sample variances of 5 and 25. Test at the 5% significance level. We've got H0 and we've got H1 here. Now we need to note that population Y has the largest sample variance. Now strictly speaking, that should be the first one, the first variance that we write down, so it should really be that way around, but with equals it doesn't matter which way around it's written, it's the same thing. And then with H1, you know, we'd write the largest sample variance first, greater than the smaller sample variance. But again, that's exactly the same as what's written here. It's just flipped around. So it's strictly speaking, it's in the format that we want, just with things written slightly differently. But I'm just going to write it this way, be consistent with what I've said, and put the largest sample variance first at the beginning there and greater than here. Now I'm going to work out my test statistic, which is going to be the sample variance of population Y divided by population X. That's 25 over 5. So 5 is the value I'm going to look to see whether it's in the critical region. I want my degrees of freedom. So remembering that my first degree of freedom is the first one that I write down here, the one with the largest sample variance. So what was that? So that's going to be Y. So that's going to be the 11, isn't it? That's the one that comes first. That's got the largest sample variance. So that comes first. So new 1 is equal to 11 minus 1. So it's important we get this the right way around. Yeah, so basically that one came from the variance or the sample variance that was the largest. That's always going to be my first degree of freedom. Then my second degree of freedom is going to be from the population that has the smaller variance, and that is the first population X. So that's going to be 7 minus 1, which is 6. Okay, so now I'm ready to find my critical values, or critical value. Now, because I've flipped this around, I've basically turned it into an upper tail test. If I kept it the way it was, it would be a lower tail test. So again, I'm just going to draw my distribution like this. I've made it an upper tail test at 5%. So this area at the top here is going to be 5%. So I want an upper critical value, and that's going to be from an F distribution with 10 and 6 degrees of freedom at the 5% mark, because it's always on the right hand side. And from the table, that's 4.06. So this value here is 4.06, and I've got a test statistic of 5. So 5 is in the critical region. So I'll say something like, since 5 is greater than 4.6, it is in the critical region. Therefore, there is sufficient evidence or enough evidence to reject H0. Then we can say, so we can just write this, can't we? The variance of population X is less than the variance of population Y, I guess, or we could just write it the other way around as we've written it like this. But I suppose, strictly speaking, we should write down the same thing as given in the question, but these are basically the same thing, aren't they? Example 11. 2 samples of sizes 11 and 13 are taken from normal distributions X and Y with variances sigma squared X and sigma squared Y respectively. The 2 samples give values of 1.6 and 2.4. test at the 10% level of significance, and we've been given H0 and H1. So in this case, we have population Y has the larger or largest variance or sample variance, 2.4, larger sample variance of 2.4. Now I know H0 and H1 are written, I'm just going to write them down again. So H0, as always, is that the population variances are the same, and H1 is going to be that the population variances are not equal. Anytime we have not equal, whatever type of hypothesis test, we know this is going to be two-tail. So we're going to be splitting the significance level of that 10% into 2 5s. Now, to be consistent with what I've said before, the larger variance I'm going to do first and have Y and X, Y and X. Okay, doesn't make any difference. These are still exactly the same hypotheses as these. Now I'll calculate my test statistic, which is going to be the larger sample variance divided by the smaller sample variance. So 2.4 divided by 1.6, that's going to be 1.5. I'm going to work out my degrees of freedom. So nu1 is from the sample that gives the larger variance. Okay, so that's my sample Y, and that had 13. Sample of 13, so 13 minus 1. So be careful not to mix these up. And nu2, my second degree of freedom, is going to be from the population that has a smaller sample variance, that's population X, and population X had a sample of 11, so that's 11 minus 1. So I'm going to find my critical values by using the F distribution with 12 and, oh actually I didn't finish off that sum, did I? 11 minus 1 is 10. Yeah, F distribution with 12 and 10 degrees of freedom. And we'll start off by finding the lower value. Before I do that, I'd just like to do a little sketch so I can see what I'm looking at. So here's my F distribution here. I'm going to be finding these critical values here, where the areas in the tails are 5%. So 5% here and 5% here. Now this brings me on to a point you need to watch out for actually, in that even though it is a two-tail test, we only need to test the upper tail. So upper tail only. Our test statistic is only going to be drifting into the upper tail since we've taken the larger sample variance and divided by the smaller. So we're always going to get like a larger value, something greater than 1 up here. So if anything, it's going to drift into the upper tail. Now if we had done this the other way around, where we've got the smaller one at the top, 1.6 over 2.4, then it would have a tendency to drift into the lower tail. So we only need to do an upper tail test because we've got the larger over the smaller, and if anything, if these variances are starting to drift apart in size, then actually this value here is going to get bigger. So we only need to do an upper tail test here, which makes it actually easier because we don't need to do the reciprocal thing or anything like that. So it's going to be the 5% that's on the right hand side here. So we can look this up in the table, and that gives a value of 2.91. So that means that this value here is 2.91. Our test statistic was 1.5, so it's over here. It's not in a critical region. Okay, so we'll say that 1.5 is less than 2.91. Therefore, it is not in the critical region. And I'll just put CR for critical region. So there is insufficient evidence to reject H0, therefore, and we can just write here that the variances of x and y are the same, or actually write that the variances are equal. Variances are equal. Example 12. A manufacturer of wooden furniture stores some of its wood outside and some inside a special store. It is believed that the wood stored inside should have less variable hardness properties than that stored outside. A random sample of 25 pieces of wood stored outside was taken and compared to a random sample of 21 similar pieces taken from the inside store with the following results. So we've got our sample sizes here. Then on the next row we have the mean hardness, and this is from coded units, and we've got these means here. And at the bottom here we've got the sum of the squares about the mean. Now I think it's worth explaining or trying to work out what these are. So it's the sum of, okay, and it's the sum of something squared, and it says the squares about the mean. Okay, so that's the difference between our observed data and the mean, the actual data and the mean. So this bottom row, this is actually what it is. It's the sum of x minus x bar all squared. And we'll start with part A, where we want to test at the 5% level of significance whether the manufacturer's claim or belief is correct. So the first thing we need to do is to calculate the variances for outside and inside. So I'm going to call this outside here. So variance of outside and then variance of inside. Now since I have this value here, to find the variance for our sample, I can simply do this, the sum of x minus x bar all squared over n minus 1. So this is a form of the equation that we can use to find the variance of our sample, but I have been given this total here. So for outside, that's going to be 5190 divided by n minus 1, 25 minus 1, or 24. And that's 216.25. And then the variance for inside, that will be 3972 divided by n 21 minus 1, so 3972 divided by 20, and that's 198.6. Right, so from here I can see that outside has the biggest variance, so now I can carry on with the hypothesis test. So it's going to be the variance of the outside population is equal to the variance of the inside population. That would be for H0 and H1. We look at the person's statement here. It is believed that the wood stored inside should have less variable properties than that outside. So inside variance, I'll just use I for variance, should be less than the outside variance. So I want to write it with the largest variance first, so just flip that around. Variance of outside greater than the variance inside. I'll now calculate my test statistic and work out whether it's in the critical area or not, and that is going to be, remember, my larger variance 216.25 divided by my smaller variance 198.6, and that gives me 1.0 0, it's like 8, 8, 8, 7, and so on. Okay, so I'll just keep that value there. Now I want to work out what my degrees of freedom are for my F distribution. So the one with the larger variance, which is the outside population, was a sample of 25, so that's going to be 24. And for the inside, nu2, that was 21, so that's going to be 20. And we're testing at the 5% level of significance. So I've drawn my little sketch here just to help me. So if I look up in the table, 24 columns across just before the last column and 20 down, I get a critical value of 2.08. So there's my critical value. So I'll put 2.08 here. And what did I have for my test statistic? 1.08. So that's going to be like sort of here. So 1.088 so on is less than 2.08, not in critical region, not enough evidence to reject H0. So something like this here, that the variance outside or inside is no difference, or you could write something like storing the wood outside makes no difference to its variable hardness than inside. I just shortened it to this because I've run out of space, but try and, well, always write a sentence in the context of the question. So you want to mention about wood being inside or outside and variable hardness properties as well. And part B, state an assumption you have made in order to do this test. Well, that both populations are normally distributed. Both populations are, can't even say distributed, normally distributed. Now in previous examples it said that the populations were normally distributed. If it doesn't tell you that and it asks for assumption, then that's going to be what you write down. We only do these tests on variances where the populations are both normally distributed. You should now be able to do exercise 60, which you'll find on pages 157 to 159 of the textbook, then followed by the mixed exercise.